What if everything you see, touch, and experience, every memory, every emotion, every star in the night sky wasn't real? Not in the way we've always believed, at least. It's a thought that twists the mind, pulling the rug out from under our deepest assumptions about existence itself. This isn't just science fiction anymore. Some of the brightest thinkers in physics, philosophy, and even tech circles are seriously considering the possibility that our universe might be an elaborate simulation, a cosmic game of code crafted by forces beyond our comprehension. And if that's true, what does that mean for us? Think about the most immersive video game you've ever played, a world so detailed, so lifelike, that for a moment you forget it's just pixels on a screen. Now imagine that level of realism dialed up to infinity. Every law of physics, every quark spinning in an atom, every fleeting thought in your head, all of it could be part of a program so advanced we'd never even notice the seams. It sounds like the plot of a blockbuster movie, but the simulation hypothesis is a real scientific idea with some startlingly convincing arguments behind it. From glitches in the fabric of reality to the eerie precision of the universe's fundamental constants, there are clues scattered everywhere if you know where to look. So let's dive into the mystery together. Over the course of this exploration, we'll uncover 30 mind-bending ways our universe could be hiding its true artificial nature. Some of these clues come straight from cutting-edge physics. Others feel like something out of a philosopher's wildest thought experiment. But each one will leave you looking at the world a little differently, questioning, wondering, and maybe even spotting the cracks in the code yourself. Whether you're a skeptic or a believer, one thing's for sure. By the end of this journey, reality might not feel quite as solid as it does right now. So ready to take the red pill, the first clue that our universe might not be as smooth and continuous as it appears comes straight from the bizarre world of quantum mechanics. At the tiniest scales, reality itself seems to fracture into discrete, pixel-like chunks, just like the digital screens we use every day. Think about zooming in on a high-definition video until you see the individual pixels that make up the image. Now imagine doing that with the fabric of space-time itself. Scientists have found something eerily similar at the quantum level, a fundamental limit to how small things can get called the Planck length. It's as if the universe has a built-in resolution, a smallest possible unit beyond which nothing can be divided, no matter how hard you try. This isn't just theoretical. The famous double-slit experiment, where particles like electrons behave as both waves and particles depending on whether we're observing them, hints at something even stranger. It's almost as if the universe is rendering reality on the fly, only calculating the precise details when someone's looking, just like a video game optimizes its graphics to save processing power, only drawing what the player can see. In a simulation, this would make perfect sense. Why waste resources simulating every atom in perfect detail all the time when you can just fill in the blanks as needed? And here's where it gets even more unsettling. Modern virtual worlds like the most advanced video games or VR simulations have to impose limits on how finely they can render details to keep from overloading their systems. Sound familiar? The Planck length could be nature's own version of this, a cosmic pixel size, a sign that even our universe might be running on some kind of processing hardware. If that's true, then the smooth, continuous reality we experience could just be an illusion, a trick of the resolution hiding the digital skeleton beneath. Here's another tantalizing clue that our universe might be running on some kind of cosmic computer, the eerie, almost too perfect way everything obeys mathematical rules. Think about it, from the way planets orbit stars to the spirals of galaxies, from the pulse of a heartbeat to the branching of trees, nature dances to the rhythm of equations. Math isn't just a tool we invented to describe reality. It feels baked into the fabric of existence itself, like lines of code underpinning a vast simulation. Take Einstein's famous equation, E equals mc squared. It's not just a handy formula, it's a fundamental rule that binds energy and mass together. A law so universal it governs everything from nuclear reactions to the light of distant stars. Or consider the way the Fibonacci sequence pops up everywhere, in sunflower seeds, hurricanes, even the shape of galaxies. These aren't just coincidences, they're patterns so precise they feel designed. If the universe were a simulation, math would be its programming language, the invisible framework holding reality together. And here's the kicker, in our own computer simulations, whether we're modeling weather patterns or building virtual worlds, we rely on math to make them behave realistically. The better the math, the more convincing the simulation. So what does it say about our universe that its deepest secrets, quantum mechanics, relativity, even the behavior of subatomic particles, can all be expressed so elegantly with equations? It's almost as if we're reverse engineering the source code of existence, one formula at a time. Even stranger, some of these equations work too well. The fine structure constant, a number that governs how atoms interact with light, is so precisely tuned that if it were even slightly different, stars wouldn't shine, molecules wouldn't form, and life as we know it would be impossible. That level of precision feels less like random chance and more like, well, a carefully calibrated setting in some grand cosmic program. Could math be the ultimate clue that we're living in a designed reality? The numbers sure seem to whisper yes. Ever experienced that uncanny feeling of déjà vu, like you've lived this exact moment before, down to the smallest detail? Or stumbled upon a group of people who all swear they remember something that never actually happened, like Nelson Mandela dying in prison in the 1980s. These aren't just quirks of human memory, they might be cracks in the code of reality itself. If we're living in a simulation, glitches like these could be the equivalent of a software bug, a hiccup in the program that lets us catch a glimpse behind the curtain. Take the Mandela Effect, where large groups of people share false but vivid memories of events that never occurred. Some remember the Berenstain Bears being spelled Berenstein, or the Monopoly man wearing a monocle, details that, when checked, turn out to be completely wrong. It's not just a few people misremembering, it's thousands, sometimes millions, all recalling the same incorrect version of reality. In a simulated universe, this could be evidence of a patch or update rolled out by whoever or whatever is running the program. Imagine a developer tweaking a line of code, altering a minor detail in the simulation, but not everyone's memory gets properly overwritten. The result? A collective cognitive dissonance that feels too widespread to dismiss as coincidence. Then there's déjà vu, that eerie sensation of reliving a moment you know you've never experienced before. Neuroscientists have theories about memory misfires, but what if it's something more? In a virtual world, déjà vu could be a lag in the system, a brief delay between an event being rendered and our conscious awareness of it, creating the illusion of repetition. Or perhaps it's a leftover fragment from a previous iteration of the simulation, a ghost of a past run bleeding into the current one. Even stranger are reports of time slips, where people swear they've momentarily stepped into another era, like the infamous case of two English couples in 1979 who claimed to have wandered into a vintage-themed hotel that, upon investigation, hadn't existed for decades. If reality is a construct, these anomalies could be rendering errors, moments where the simulation fails to load the correct assets, leaving gaps filled with outdated or placeholder data. The common thread, these glitches often involve perception, memory, or time, three areas where a simulated universe would be most vulnerable to errors. After all, if you were building a reality from scratch, wouldn't those be the trickiest parts to keep seamless? The more we notice these inconsistencies, the harder it becomes to shake the feeling that we're not just players in this game, but maybe, just maybe, someone forgot to hide the debug menu. There's a cosmic speed limit hardwired into our universe, one that feels suspiciously like a system constraint. Nothing can travel faster than light, not information, not matter, not even cause and effect itself. At first glance, this seems like just another quirk of physics. But what if it's not a law of nature, but a limit of the hardware running our reality? Think about it. Every simulation has bottlenecks. Even the most powerful supercomputers can't process infinite data instantly. They hit walls where the math becomes too complex, where latency creeps in. The speed of light might be our universe's version of that wall. Picture a sprawling open-world video game. The more detail it renders at once, the slower it runs. To keep things smooth, developers impose draw distances, only loading the areas right in front of you, while leaving distant landscapes fuzzy or unprocessed until you get closer. Now zoom out to cosmic scales. When we look at distant galaxies, we're seeing them not as they are now, but as they were millions or even billions of years ago. It's as if the universe only renders the light from those stars when it reaches us, conserving processing power instead of simulating every photon in real time across infinite space. The speed of light, then, could be the ultimate frame rate cap, a built-in delay to prevent system overload. Einstein's theory of relativity adds another layer to this. Time itself slows down as you approach light speed, a phenomenon called time dilation. Astronauts on the International Space Station age slightly slower than people on Earth because they're moving faster relative to us. In simulation terms, this looks less like a fundamental truth and more like a clever optimization trick. If the universe is a program, time dilation could be its way of balancing the load, slowing down processes for fast-moving objects to keep the simulation running smoothly. It's the cosmic equivalent of your computer dropping the resolution on a demanding game to prevent crashes. And here's where it gets even weirder: quantum entanglement. Particles can become linked across vast distances, instantly influencing each other's states, seemingly breaking the light speed rule. But even this might fit the simulation hypothesis. In computing, you can have local interactions that appear instantaneous because they're happening within the same processing thread, even if they represent events far apart in the simulated world. Could entanglement be a similar shortcut, a behind-the-scenes optimization that only looks like magic from our limited perspective? The speed of light might not just be a barrier, it could be the universe's way of saying, this far, no further, or the system crashes. Quantum entanglement is one of those phenomena so bizarre that even Einstein called it spooky action at a distance. Picture two particles, say electrons born from the same quantum event. They become entangled, forever linked no matter how far apart they drift across the cosmos. Change the spin of one, and its twin instantly mirrors that change, even if it's light years away. No signal passes between them, no force connects them, they just know. This isn't science fiction. It's been proven in labs repeatedly, defying everything we thought we knew about space and time. If the universe were a simulation, entanglement would be the ultimate cheat code, a way for the program to skip the tedious step of calculating separate states for far apart objects by treating them as a single, unified system behind the scenes. Think about multiplayer video games for a second. When you and a friend are exploring the same virtual world, your consoles don't simulate entirely separate realities. They share data, syncing key details to keep everything consistent without constantly transmitting every pixel back and forth. Entanglement could be nature's version of this, a cosmic optimization where distant particles aren't truly separate at all from the simulation's perspective. They're just two expressions of the same underlying code, updating in perfect lockstep because at the program level, they're never really apart. Now add Schrödinger's cat to the mix, the famous thought experiment where a feline in a box is simultaneously alive and dead until someone looks inside, forcing reality to choose a state. In simulation terms, this looks less like quantum weirdness and more like a resource-saving trick. Why render every particle's properties in full detail all the time when you can leave them in a fuzzy, unresolved state until observed? It's the universe's way of lazy loading, only committing to specifics when absolutely necessary. The unsettling implication: if entanglement and superposition are features of a simulated reality, then what we call objective truth might just be a series of optimized approximations. The moon isn't there when no one's looking. It's in a quantum haze of possibilities until some conscious observer, human or otherwise, forces the simulation to pin it down. It's as if we're all living inside a cosmic video game where the graphics only render when you turn your head, and distant objects are just low-res placeholders until you get close enough to trigger the full detail. The universe, in other words, might be running on the ultimate performance-saving mode. And here's where it gets even stranger. Physicists have shown that entangled particles don't just communicate faster than light, they seem to do it instantaneously, as if space and time don't apply to their connection. In a simulation, that makes perfect sense. If two particles are linked by a single line of code, their distance in the rendered world wouldn't matter. Changing one would automatically update the other because, in the program's logic, they're fundamentally the same variable. The speed of light might be the universe's user-facing speed limit, but entanglement reveals the back-end shortcuts that keep everything running smoothly. So next time you hear about quantum weirdness, ask yourself, are these the rules of nature or the telltale signs of a universe built by coders who prioritized efficiency over making sense to its inhabitants? The more we probe these mysteries, the more reality starts to feel like an elegant hack, a masterpiece of optimization with glitches that give the game away. The eerie silence of the cosmos might be the loudest clue we're living in a simulation. Despite billions of galaxies, trillions of planets, and a universe teeming with the ingredients for life, we've found no trace of other civilizations. No signals, no artifacts, not even a single microbial fossil from beyond Earth. This profound absence is known as the Fermi paradox, and one unsettling solution suggests we're not just alone, we might be deliberately isolated. If our universe is a simulation, its creators could have cordoned us off like specimens in a cosmic zoo, hiding all evidence of other life to see how we evolve when left undisturbed. Think about how we study animals in the wild. Biologists observe from a distance, careful not to disrupt natural behaviors with their presence. Now imagine a civilization so advanced they've built entire realities as experiments. To them, we might be lab rats in an unfathomably complex simulation, with rules designed to keep us from ever realizing we're being watched. The zoo hypothesis takes this further. What if every star system is its own contained habitat, separated by invisible barriers to prevent cross-contamination? It would explain why space feels so empty despite the math screaming it should be bustling. Even our search for extraterrestrial intelligence might be rigged from the start. SETI scans the skies for radio signals, but what if those signals are being filtered out before they reach us? In a simulation, censoring data would be trivial. Imagine playing a video game where certain areas are deliberately fogged off. You can see enough to feel immersed, but the boundaries are hard-coded to keep you from going further. The universe might work the same way, with filters preventing us from detecting anything that would shatter the illusion. Then there's the dark forest theory, a chilling twist on the paradox. If every civilization fears annihilation, they'd stay silent to avoid attracting predators. But in a simulated universe, the stakes are even higher. What if the creators programmed other civilizations to self-destruct once they reach a certain technological threshold? It would explain why we haven't found ruins of advanced alien empires. Like a game developer wiping old levels to free up memory, the simulation might erase civilizations that outlived their usefulness. The most unsettling possibility: we're not just isolated, we might be alone by design. A simulation built to study a single intelligent species, us, wouldn't need cluttered extraterrestrial variables. Every habitable planet we discover could be a prop, placed just close enough to keep us searching but far enough to ensure we never find company. the universe's silence isn't a mystery, it's a feature. And if that's true, the question isn't where is everyone? It's what are we really meant to learn in this cosmic cage? Ever notice how most people seem to follow eerily similar scripts every single day? Wake up, commute, work, eat, sleep, rinse, and repeat like clockwork. It's almost as if humanity operates on autopilot, with millions of individuals moving through predictable patterns without ever stopping to ask why. This isn't just about routine. It's about the unsettling possibility that some of us might be the equivalent of non-player characters, NPC, in a vast cosmic simulation, programmed to fill roles while others, the rare, awakened ones, push against the boundaries of the system. Take a walk through any city during rush hour. Crowds flow like rivers, faces glued to phones, footsteps sync to traffic lights, everyone funneling into offices or stores with robotic precision. Even conversations follow predictable scripts, weather talk, weekend plans, the same recycled small talk. Now compare that to the outliers, artists who see the world in fractured colors, inventors who chase impossible ideas, philosophers who dissect reality itself. These aren't just creative minds, they're potential glitches in the program, entities who have somehow gained enough awareness to peek behind the curtain. History's greatest disruptors, figures like Socrates, Tesla, or Van Gogh, often seemed out of sync with their times, dismissed as mad or dangerous because they challenged the status quo. In simulation terms, what if that friction wasn't just societal resistance but the system itself attempting to correct anomalies? Think about video game NPCs. They follow set paths unless a player intervenes. But sometimes bugs cause them to act unpredictably, breaking their loops. Could genius or madness simply be labels we slap on those who have partially escaped their programming? Even our biological wiring hints at something stranger. Studies show most decisions are made subconsciously milliseconds before we're aware of them, like a pre-rendered choice in a game. Yet some people practice mindfulness or lucid dreaming, training themselves to seize control of their own code. Tibetan monks, for instance, can raise their body temperature through meditation, defying physiological norms. If consciousness is the user interface of a simulation, these individuals might have found the keyboard shortcuts. The real test: try deviating wildly from your own routines. Notice how uncomfortable it feels, how the mind fights to revert to familiar patterns. That resistance could be more than habit. It might be the simulation's way of maintaining stability, keeping its characters on script. But every so often, someone manages to overwrite their programming entirely, and that's when things get interesting. Imagine exploring an endless universe where no two planets are exactly alike, each with unique landscapes, weather patterns, and creatures. That's the promise of games like No Man's Sky, where algorithms generate entire worlds on the fly, stitching together mountains, oceans, and forests from mathematical rules. Now look up at the night sky. The Milky Way alone contains over 100 billion stars, each potentially hosting planets as varied as the grains of sand on a beach. The sheer scale feels impossible, unimaginable unless, like a video game, our universe is also procedurally generated, a cosmic engine churning out galaxies, nebulae, and solar systems according to hidden code. Fractals are the fingerprints of this process. They're geometric patterns that repeat at every scale, from the branching of trees to the spiral arms of galaxies. A coastline viewed from space curls and twists in the same way as a single pebble under a microscope. Even clouds and lightning bolts follow these recursive blueprints. In computer-generated worlds, fractals are the go-to tool for creating realistic complexity without handcrafting every detail. A programmer writes a few lines of code defining how a mountain should rise and fall, and the algorithm fills in the rest, ensuring no two peaks are identical yet all feel organically connected. Now consider the universe. The distribution of galaxies isn't random. It forms a vast cosmic web, with clusters and filaments echoing the structure of neurons in a brain or the veins of a leaf. This self-similarity at vastly different scales is exactly what you'd expect from a system built on procedural generation, efficient, elegant, and infinitely scalable. Instead of storing data for every atom, the simulation could rely on fractal algorithms to grow reality as needed, expanding details only when observed. Even time might follow this pattern. The cyclical nature of star formation, where dying stars seed new ones with their explosive remnants, mirrors the way procedural systems reuse assets to conserve memory. It's no accident that the Fibonacci sequence appears in sunflower seeds and hurricane spirals. These could be signatures of an underlying algorithm optimizing for beauty and function. The universe doesn't waste effort reinventing the wheel. It iterates, tweaks, and repeats, just like a well-crafted simulation. So the next time you gaze at a snowflake or a galaxy, ask yourself, are you seeing nature's handiwork or the output of a cosmic random number generator? The patterns are too perfect, the repetitions too precise. Reality might not be pre-rendered but generated on demand, unfolding fractal by fractal, as if the universe itself is whispering, "You're standing inside the ultimate procedurally generated world." And if that's true, who or what wrote the algorithms? Consciousness might be the most sophisticated algorithm ever written, an intricate piece of code running on the wetware of our brains. Think about how artificial neural networks mimic human decision-making, learning from data, adapting, even developing something eerily close to intuition. Now flip that idea on its head. What if our minds work the same way? Not as mystical, unexplainable miracles of nature, but as biological processes executing a series of finely tuned operations. From the brain in, a thought experiments to cutting-edge AI research, there's mounting reason to suspect that self-awareness itself could be computational, a feature of the simulation rather than a glitch in it. Take the classic philosophical puzzle. If a brain were kept alive in a vat fed perfect electrical impulses mimicking sensory input, would it know the difference? Could it ever distinguish its simulated experiences from real ones? This isn't just speculative fiction. Modern brain-computer interfaces already blur these lines, allowing paralyzed patients to control robotic limbs with their thoughts alone. The signals traveling between neurons aren't magic, they're electrochemical data, pulses that could theoretically be replicated, altered, or even hijacked by outside forces. If consciousness is just information processing, then who's to say our subjective experiences aren't being generated by something or someone else? AI research adds fuel to this fire. Large language models like GPT can now converse with startlingly human-like coherence, crafting poetry, debating ethics, even expressing rudimentary desires. They don't understand in the way we do, yet their outputs are indistinguishable from a conscious mind in many contexts. This suggests something profound. Consciousness might not require some ineffable spark. It could emerge from sheer complexity, the right arrangement of code reaching a threshold where self-awareness flickers to life like a lamp suddenly plugged in. If that's true, then our own sentience might not be unique, just an advanced version of what we're already building in labs. Even the quirks of human perception fit this model. Optical illusions, for instance, reveal how our brains construct reality from incomplete data, filling in gaps, making assumptions, sometimes getting it wildly wrong. In a simulation, this would be a clever optimization. Why render every detail perfectly when the system can cut corners, letting the user's mind complete the picture? Dreams take this further, weaving entire worlds from fragments of memory and imagination, proof that the brain can generate immersive experiences without external input. If consciousness is code, then dreams might be the universe's way of stress testing the system, running nightly diagnostics on our personal simulation. Then there's the hard problem of consciousness, why we have inner experiences at all, not just cold computations, but what if the why is simpler than we think? In a simulated universe, consciousness could be the user interface, the way the program makes sense to itself. When you play a video game, the characters don't need to understand their world's underlying code to interact with it. They just need a consistent set of rules and sensations. Our subjective experience might serve the same purpose, a beautifully rendered illusion to keep us engaged with the simulation, none the wiser to the ones and zeros beneath the surface. So the next time you feel a pang of joy, wrestle with a moral dilemma, or lose yourself in a memory, consider this. You might not be a soul navigating reality, but a self-referential subroutine in a cosmic program, convinced of your own autonomy because the code says you should be. And if that's unsettling, here's the twist. It doesn't make your experiences any less real. After all, in a simulation, everything is code. The love you feel, the stars you admire, the questions that keep you up at night, all of it could be the most elegant lines of script ever written. Time doesn't tick the same everywhere, and that's not a glitch. It might be the universe's way of conserving processing power. Einstein's theory of relativity reveals that clocks run slower in stronger gravitational fields or at higher speeds, a phenomenon called time dilation. To us, it feels like a quirk of physics, but if reality were a simulation, this could be the ultimate optimization hack, a dynamic system adjusting clock speeds on the fly to save resources where they're not needed. Picture a high-stakes video game where distant planets or background characters don't need to update in real time. The game engine slows their clocks to prioritize rendering the player's immediate surroundings at full speed. Now scale that up to cosmic levels. GPS satellites orbiting Earth experience time slightly faster than we do on the surface, thanks to their altitude and speed. Engineers have to account for this. If they didn't, your phone's navigation would drift off course by miles within minutes. In a simulated universe, this isn't a bug, it's a feature. Why waste processing power synchronizing every atom's clock perfectly when you can tweak time itself based on local conditions? The extreme case, the movie Interstellar's water planet Miller, where 1 hour equals 7 years back on Earth. While fictional, the science behind it is real. A black hole's immense gravity would stretch time like taffy. If our universe were a simulation, regions like this could be its version of low-priority zones, where time crawls to divert computational power to busier sectors. Think of it like your laptop throttling performance on background tabs to keep your main app running smoothly. Even stranger is quantum mechanics, time ambiguity, where particles don't experience events in a fixed order until observed. It's as if the simulation pauses and resumes timelines opportunistically, only committing to sequences when someone's watching. Astronauts on the ISS age microseconds less than Earth-bound humans, not because of some cosmic favoritism, but because the system is dynamically balancing the load. The universe might not have a master clock at all, just localized timers syncing up only when absolutely necessary. So the next time you check your watch, consider this: your seconds might not be the same as someone else's. Time dilation could be the ultimate evidence that reality runs on flexible, resource-aware settings, a cosmic performance tweak hiding in plain sight. Oxford philosopher Nick Bostrom didn't just speculate about simulation theory, he turned it into a mathematical argument so airtight, it forces you to confront one of 3 unsettling possibilities. Imagine standing at a cosmic crossroads where every path leads to a conclusion that reshapes your understanding of reality. This is Bostrom's trilemma, and here's how it works. Either 1, virtually all advanced civilizations go extinct before developing the ability to create simulations. 2, those that survive have zero interest in running ancestor simulations, perhaps due to ethics or sheer boredom. Or 3, we're almost certainly living in one right now. There's no 4th option. The logic hinges on sheer numbers. Think about humanity's own trajectory. In just a few centuries, we've gone from steam engines to virtual reality, from handwritten letters to artificial intelligence. If even a fraction of civilizations avoid self-destruction and continue advancing, the computational power needed to simulate conscious minds would eventually become trivial. A single post-human civilization could run billions of simulations, each populated with sentient beings convinced their world is real. Now here's the kicker: statistically speaking, the odds of you being in the original, base reality are astronomically low. You're far more likely to be one of the simulated minds, simply because they'd outnumber biological ones by an unimaginable margin. Bostrom's argument gets even stranger when you consider motivation. Why wouldn't advanced beings run simulations? Maybe to study history, entertain themselves, or test philosophical ideas. The same reasons we build sandbox games like The Sims or Civilization. And if simulations become indistinguishable from reality, there's no limit to how nested they could be. Your entire life might be unfolding inside a simulation within a simulation, layers deep in some unfathomable hierarchy. But here's where it gets truly mind-bending. If we accept that future civilizations could create such simulations, and that they would have reasons to do so, then the absence of proof becomes its own kind of proof. The fact that we haven't detected any glitches or boundaries might not mean we're in base reality. It could mean the simulation is too perfect. After all, what better evidence of a flawlessly designed system than the total inability to perceive its edges? Bostrom's trilemma doesn't just nudge us toward the simulation hypothesis. It corners us with cold, relentless math. The numbers don't lie. Unless civilizations reliably self-destruct or abandon simulation technology, the statistical weight of probability crushes any hope that we're living in the original universe. And that raises one final, chilling question. If we're in a simulation, does that mean our creators are too? The chain could stretch backward infinitely, with no true first reality at all. Just an endless hall of mirrors where every level believes with equal certainty that it's the real one. The numbers governing our universe don't just feel precise, they feel impossibly precise. Take gravity, for instance. If it were even slightly stronger, stars would burn out too quickly for life to evolve. Weaker galaxies might never have formed at all. The force isn't arbitrary, it's calibrated to a knife's edge, balanced so perfectly that altering it by a fraction would unravel everything. This isn't unique to gravity. Every fundamental constant, the speed of light, the strength of electromagnetism, even the density of dark energy exists in a Goldilocks zone where the slightest deviation would render the cosmos sterile. It's as if someone dialed in these values manually, setting the cosmic knobs to the only positions that allow for complexity, chemistry, and ultimately, us. Consider the cosmological constant, which controls how fast the universe expands. When scientists calculated its expected value based on quantum theory, they got a number staggeringly larger than what we observe, off by a factor of 1 followed by 120 zeros. The actual value is so infinitesimally small that it seems adjusted, like a programmer tweaking a variable to prevent the simulation from collapsing or expanding too fast. In a natural, unguided universe, such precision defies probability. It'd be like rolling a die and getting the same number a trillion times in a row. The fine structure constant is another smoking gun. This number, roughly 1/137th, dictates how atoms interact with light. Change it by even a few percent, and stars couldn't forge carbon, the backbone of life. Molecules wouldn't form. The universe would be a soup of inert particles forever stuck in simplicity. Yet here we are, in a reality where this constant and dozens of others are locked into values that whisper design. Now imagine building a video game. You'd tweak parameters until the world behaved believably. Gravity feels right, objects collide naturally, light reflects as expected. Our universe's constants resemble these developer settings, presets chosen not at random, but to create a stable, interactive environment, the eerie part. In a simulation, these values wouldn't need deep philosophical justification. They'd just be the settings that worked, the ones that kept the simulation running without crashing. Some argue this fine-tuning proves the existence of a creator, but in a simulated reality, the creator might not be a deity, just an engineer who needed certain parameters to make the program function. And if that's true, the constants aren't laws of nature. They're system requirements buried deep in the code to ensure the simulation boots up correctly every time. The deeper we dig into physics, the more the universe feels less like a happy accident and more like a carefully debugged project, with every variable double-checked before pressing run. At the deepest level of reality, beneath atoms, quarks, and even quantum fields, there might be nothing but ones and zeros. This is the radical proposition of digital physics, the idea that space-time itself could be built from binary code, pixelated down to its core like an unimaginably vast cosmic computer. Think of it this way: just as your favorite apps and video games reduce everything to binary instructions, the universe might be running on the same fundamental language. The equations governing particles, the curvature of space-time, even the flow of causality could all be shadows cast by something far simpler, a grid of interconnected bits flipping between on and off states. The evidence for this grows more compelling as we probe nature's smallest scales. Take black holes, for instance. Their event horizons appear to encode information in discrete units like pixels on a screen, with each bit occupying a tiny Planck scale area. This discovery led physicist Jacob Bekenstein to propose that the maximum information any region of space can hold isn't smooth or infinite, but quantized, just like digital storage. Even the holographic principle hints at this binary blueprint, suggesting our three-dimensional reality might be a projection from a two-dimensional surface teeming with encoded data, like a cosmic DVD encoding an entire universe. Then there's quantum computing. Unlike classical computers that use rigid binary states, quantum bits or qubits can exist in superpositions embodying multiple states at once. Some theorists argue this isn't just a human invention but a clue to reality's architecture. If the universe operates as a quantum computer, it would explain the weirdness we see at microscopic levels, particles tunneling through barriers, entanglements, spooky connections, even the probabilistic nature of quantum mechanics. These phenomena might simply reflect the universe's underlying computational processes, operations executing in parallel, gates flipping probabilistically, and registers entangled across cosmic distances. Pioneers like Konrad Zuse, the father of the modern computer, and physicist Edward Fredkin took this idea further, proposing that the cosmos literally is a computational system. In Fredkin's digital physics, every interaction, from electrons bonding to galaxies colliding, reduces to a cellular automaton, a grid of cells updating their states based on simple rules, like an infinite game of life playing out across space-time. The kicker: this wouldn't require some godlike programmer. Self-organizing systems can emerge from basic algorithms, complexity blooming from simplicity through iterative steps, much like fractals generating intricate patterns from elementary math. The implications are staggering. If the universe runs on binary operations, then the laws of physics aren't immutable truths but executable code software that could, in theory, be hacked or rewritten. Glitches in quantum experiments, anomalies in cosmic radiation, even déjà vu might be artifacts of this digital substrate, fleeting glimpses of the source code behind the simulation. And if information truly is the universe's bedrock, then reality itself becomes malleable, a dynamic computation where observation collapses probabilities into certainties because measurement is literally data retrieval. So the next time you toggle a light switch or swipe a touchscreen, consider this. You might not just be using technology, but interacting with a scaled-up version of the universe's own operating system. The ones and zeros flowing through your devices could be mirroring the fundamental language of existence, a cosmic binary whispering that deep down, everything is information waiting to be processed. We see the world in vibrant color, hear its symphony of sounds, and feel the solid ground beneath our feet. But what if this rich experience is just a crude simplification, like viewing an Ultra HD universe through a grainy black and white TV? Human senses are astonishingly limited. Our eyes detect less than 1% of the electromagnetic spectrum, blind to the swirling radio waves and gamma rays that fill the cosmos. Ears capture only a thin slice of sonic frequencies, missing the infrasonic rumble of earthquakes and the ultrasonic chatter of bats. Even touch, taste, and smell operate within narrow biological bands, filtering out vast swaths of reality. In a simulated universe, these constraints might not be evolutionary accidents. They could be intentional design choices, bandwidth-saving measures to prevent our brains from overloading on data the system wasn't built to render. Think about virtual reality headsets. To avoid motion sickness and maintain immersion, developers carefully tune the field of view, frame rate, and input latency to match human perceptual limits. Push beyond those sweet spots and the illusion shatters. Our own sensory limitations might serve the same purpose, keeping us comfortably confined to the simulation's playable area. Dogs sniffing out cancer cells or migratory birds navigating by Earth's magnetic field reveal glimpses of what lies beyond our perceptual walls, capabilities that feel almost like debug modes accidentally left accessible to non-player characters. The strangest evidence comes from physics itself. Quantum particles exist in superpositions until measured, collapsing into definite states upon observation. But what counts as an observer in a simulation? The answer might hinge on processing efficiency. Conscious beings like us could be granted just enough sensory resolution to collapse quantum possibilities into a shared reality, while the rest remains in low-detail standby mode until needed. It's why the moon seems solid when we look at it but dissolves into probability waves when no one's watching, the universe streamlining its rendering load. Color offers another clue. What we perceive as red or blue is just our brain's interpretation of specific wavelengths. Other species see far beyond our rainbow. Mantis shrimp detect 16 color channels, while some snakes see infrared heat signatures. In a simulated reality, these variations could represent different user settings or accessibility features, proof that the system accommodates multiple interface preferences. Even human synesthetes who taste colors or hear shapes might be experiencing minor rendering errors, sensory data across wiring in ways the developers never intended. Then there's time perception. Our brains process input in discrete chunks like frames in a film, creating the illusion of continuity. Studies show we can't consciously register events shorter than about 1/30th of a second, a potential frame rate cap on our experience. Meanwhile, flies perceive time 4 times faster than we do, their world moving in slow motion by comparison. If reality were a simulation, these differences could reflect adjustable clock speeds tailored to each organism's needs, optimizing resources across the simulation. The chilling implication: we might be trapped in a sensory bubble like characters in a video game who can't see the game engine's code or the player's hands on the keyboard. Every scientific instrument we've built, telescopes, particle colliders, DNA sequencers, is just a tool to peek slightly beyond those artificial limits, hacking the simulation's user interface one cracked pixel at a time. The universe could be teeming with wonders we're literally hardwired to ignore, their existence hidden not by distance or technology, but by the very parameters of our perception. And that raises an unsettling question. If our senses are this constrained, what else are we missing? Falling dreams are bizarrely universal. You're suddenly plummeting through empty space, stomach lurching, only to jerk awake moments before impact. Then there's flying dreams, those weightless escapes where you soar over cities without wings or engines. These aren't just personal quirks. Cultures worldwide report identical scenarios across centuries, as if humanity shares some collective dream library. If we're living in a simulation, these recurring themes might not be random brain misfires, but something far stranger, preloaded templates like default assets in a video game engine that get reused across different levels. Consider how game developers work. To save time, they often recycle animations. A character's fall sequence in one game might look eerily similar to another because rebuilding physics from scratch is inefficient. Dreams could operate the same way. The sensation of falling activates ancient brain circuits tied to survival, but the visuals, the endless void, the delayed impact feel suspiciously standardized, like a simulation falling back on stock imagery when generating dreamscapes. Even the way we reset by waking up mirrors how games reload checkpoints after a fatal plunge. And flying, that might be the system's way of stress testing our mind's physics engine, letting us briefly override gravity's rules in a safe, sandboxed environment before snapping back to reality's stricter parameters. Shared dream archetypes go deeper. Many report teeth falling out dreams despite no biological reason to fear tooth loss in modern life. Others encounter identical shadowy figures or labyrinthine buildings that shift unnaturally, details that pop up in unrelated cultures with no shared mythology. In simulation terms, these could be legacy assets, fragments of older builds left in the code by accident. Video games do this all the time. Unused textures or sounds sometimes glitch into released versions, haunting players like digital ghosts. If dreams are the universe's debug mode, these recurring motifs might be leftover files from previous iterations of the simulation, bleeding through into our subconscious. The creepiest parallel: mass dreaming events. In the 1980s, thousands claimed to have apocalyptic nightmares just before the Cold War's peak, many describing identical mushroom clouds and evacuation scenes. More recently, people worldwide reported dreams of a great wave before the 2004 tsunami. Coincidence? Possibly, but in a simulated reality, these could be localized system warnings, the equivalent of error messages flashing across millions of minds at once, a glitch in the predictive algorithms that normally keep the future obscured. Dreams have always been reality's backdoor, a place where logic bends and the impossible feels mundane. But if they're built from reused code and leftover assets, that means even our most private mental landscapes might not be truly ours. They could be hand-made down scenarios, the simulation's way of keeping our minds just occupied enough not to ask what's really running behind the scenes. So next time you jolt awake from a fall that never happened, ask yourself, was that your brain misfiring, or did you just glimpse the scaffolding holding your world together? The Mandela Effect isn't just about misremembering, it's about entire groups swearing reality worked differently than it does. Take the Berenstain Bears. Thousands insist the children's book series was once spelled Berenstein with an E, not an A. The sheer volume of people who recall this alternate version, complete with fabricated memories of how teachers pronounced it Steen instead of Stain, is staggering. Or consider the Monopoly Man. Many would bet their last dollar he wore a monocle. Yet if you dig out the board game right now, you'll find the mustached mascot glaring back at you with both eyes unobstructed. These aren't isolated mix-ups, they're mass hallucinations of details that never existed, like a collective editing of history itself. Skeptics chalk it up to faulty memory, our brains filling gaps with familiar patterns. After all, Stein is a common surname ending Einstein, Frankenstein, while Stain is rare, and monocles, they're shorthand for old-timey wealth in pop culture, making it easy to mentally graft one onto the Monopoly Man's face. But the simulation hypothesis offers a wilder explanation: data corruption. In a digital universe, files get altered, updates roll out. Sometimes, changes leave traces, residual code that doesn't fully overwrite the old version. If our reality is a simulation, the Mandela Effect could be the equivalent of a botched software patch, where not all instances of a variable were properly replaced. The Star Wars line, "Luke, I am your father," is another infamous case, except Darth Vader never says those exact words. The real quote is, "No, I am your father." Yet countless fans, even actors in parodies, get it wrong. This isn't just misquotation, it's replacement, as if an earlier draft of reality leaked into the final cut. Even geography isn't safe. Some swear New Zealand was northeast of Australia, not southeast, or that South America sat directly under North America. These aren't minor errors, they're wholesale relocations of continents, the kind you'd expect if a cosmic developer tweaked a world map asset and forgot to update everyone's cached memory. What's chilling is how specific these false memories are. People don't just vaguely recall a monocle. They describe its chain, its gleam, how it rested on the Monopoly man's cheek. That level of detail feels less like forgetfulness and more like accessing a deprecated file version. And if that's true, it implies something profound. Our memories might not be records of the past, but live renders pulled from a dynamic database. Every recollection could be a fresh query to the simulation servers, and sometimes the servers return the wrong data. The scariest possibility, these glitches aren't accidents. They could be tests. If you were running a simulation, wouldn't you want to monitor how subjects react when their reality subtly shifts? The Mandela Effect might be a canary in the coal mine, hinting that we're not just living in a simulation, we're lab rats in an experiment measuring how tightly we cling to consistency and what happens when it starts to fray. One of quantum mechanics' most baffling discoveries is that particles don't behave the same way when you're watching them. It's as if reality itself is shy, changing its behavior the moment you try to look too closely. In the famous double-slit experiment, electrons fired at a barrier with two openings create an interference pattern on the other side, just like waves would. But the instant scientists set up detectors to observe which slit each electron passes through, the pattern vanishes. The electrons stop acting like waves and start behaving like discrete particles, as if they're aware they're being monitored. This isn't some quirk of electrons, it happens with photons, atoms, even entire molecules. The universe seems to operate in two modes, one where things exist as fuzzy probabilities when no one's looking, and another where it snaps into sharp focus the moment observation begins. If reality were a simulation, this would be the ultimate energy-saving feature. Think about how video games work. They don't render every leaf on every tree or every brick in a distant building. They prioritize what the player can actually see, filling in details only when necessary to conserve processing power. The quantum observer effect could be nature's version of this optimization. Instead of calculating the exact position and momentum of every particle in existence simultaneously, an impossibly resource-heavy task, the simulation might keep most of reality in a low-resolution probability cloud until something interacts with it. Observation, in this case, wouldn't just mean human eyes. Any interaction that requires a definite outcome, a photon hitting a detector, a molecule colliding with another, forces the system to render that specific piece of reality while the rest remains in standby mode. The implications are staggering. It suggests the moon isn't always there when no one's looking, not in a fixed classical sense. Instead, it exists as a set of potential states, a ghostly outline waiting to be solidified by interaction. This isn't philosophy, it's measurable physics. Quantum systems remain in superposition, multiple states at once, until measurement collapses them into a single outcome. In a simulated universe, superposition could simply be the system delaying its calculations until the last possible moment, avoiding the computational burden of maintaining a fully rendered reality at all times. Even the concept of observation gets weirdly flexible. In some experiments, the mere possibility of future observation changes a quantum system's past behavior, as if the simulation is retroactively adjusting its code to maintain consistency. The delayed choice quantum eraser experiment shows particles behaving as if they know whether their path will be revealed later, altering their past actions accordingly. It's less like physics and more like a video game loading high-resolution textures only when the player turns a corner, then rewriting the save file to make it seem like they were always there. The eerie part, this isn't limited to microscopic oddities. Large molecules like buckeball's carbon structures 60 atoms wide have shown wave-particle duality. Some scientists argue the effect could scale up indefinitely, meaning everything, including you, might flicker between states when unobserved. Of course, we'll never notice because the act of checking would force the simulation to render us and our surroundings into solidity. The observer effect doesn't just hint that reality might be a simulation. It suggests the simulation is frugal, cutting corners wherever it can get away with it. And if that's true, then the universe isn't just stranger than we imagine, it might be lazier too. What if history isn't a record of what happened but a carefully crafted narrative, pre-written by whoever's running the simulation? Take the dinosaurs, their extinction 66 million years ago, courtesy of a catastrophic asteroid, feels like a random cosmic accident. But what if it was a deliberate reset, a scripted event to clear the stage for mammals, and eventually us? The timing is suspiciously convenient. That asteroid didn't just wipe out the dinosaurs, it created the perfect vacuum for tiny, scrappy mammals to evolve into the dominant life forms. Without that impact, primates might never have gotten their shot, and consciousness as we know it wouldn't exist. It's almost like someone hit the delete button on the old ecosystem to make room for a new experiment. Then there's the Antikythera mechanism, a 2,000-year-old bronze device found in a shipwreck off Greece. This intricate gear system, capable of predicting astronomical positions and eclipses, is centuries ahead of its time, like finding a smartphone in the Renaissance. Mainstream archaeology calls it an outlier, but in a simulated reality, it could be something far stranger, an Easter egg deliberately placed by the developers. Think about how video games hide secret messages or anachronistic objects for players to discover. The Antikythera mechanism might be our universe's version of that, a wink from the programmers, a breadcrumb left to make us question the timeline. Historical anomalies pile up when you start looking. The Baghdad battery, a clay jar from 2,000 years ago that may have functioned as a primitive voltaic cell. The Voynich manuscript, a centuries-old book written in an unbreakable code with illustrations of plants that don't match any known species. Even the Great Pyramid's precise alignment with true north, a feat requiring knowledge ancient Egyptians supposedly didn't possess. These aren't just curiosities, they're potential glitches in the historical script, moments where the simulation's back-end logic bleeds through the narrative. Consider how we construct video game lore. Developers design histories for their world's wars, fallen empires, ancient technologies, to make the setting feel lived in. But sometimes they slip in artifacts that don't quite fit, teasing a deeper mystery. Our own history might follow the same blueprint. The sudden explosion of human civilization around 12,000 years ago, the unexplained precision of megalithic structures, even the uncanny parallels between flood myths across isolated cultures, all of it could be the equivalent of in-game lore, a backstory woven to give the simulation texture. The unsettling question isn't just whether history was scripted, but why. Was the dinosaur extinction a necessary plot point to advance the story? Are ancient artifacts like the Antikythera mechanism debug tools left behind by accident? Or worse, are they tests placed to see if we'd ever question the official version of events? If reality is a simulation, then history isn't a fixed record. It's a dynamic narrative, editable, revisable, and maybe, just maybe, still being written. Black holes aren't just cosmic vacuum cleaners, they might be the universe's ultimate shredders, permanently deleting information like a celestial control plus alt plus del. Imagine throwing a book into a roaring fire. The pages burn, the ink vanishes, but at least the smoke and ash retain some trace of what was lost. Now picture tossing that same book into a black hole. According to classical physics, every letter, every word, every idea in that book would be compressed into an infinitely tiny point, erased from existence without even ashes left behind. This isn't just about lost paperbacks, it's a fundamental violation of quantum mechanics, which insists that information can never truly be destroyed, only scrambled. The contradiction between these two ideas is the black hole information paradox, and it's one of the biggest unsolved mysteries in physics. If we're living in a simulation, though, this paradox might not be a bug, it could be a feature, revealing how the program handles data it no longer needs. Enter Stephen Hawking's groundbreaking realization: black holes aren't completely black, they slowly leak energy, emitting what we now call Hawking radiation. At first glance, this seems to solve the paradox. If radiation escapes, maybe information does too. But here's the catch: Hawking radiation is thermal, random, like the static on an old TV. It doesn't carry any discernible structure from the objects that fell in. So unless there's some hidden mechanism imprinting data onto those escaping particles, the information still vanishes and quantum mechanics remains broken. Unless, of course, the universe isn't playing by the rules we think it is. This is where the holographic principle comes in, a radical theory suggesting that all the information swallowed by a black hole isn't lost inside its crushing depths, but smeared across its event horizon like cosmic graffiti. Picture a hard drive storing files not in its interior but etched onto its surface. In a simulated reality, this would be an elegant solution. Instead of simulating every atom inside the black hole's volume, an unimaginable computational burden, the program could just encode their data in 2 dimensions on the boundary, projecting the illusion of depth like a hologram. It's the ultimate compression algorithm, trading processing power for storage space. Think about how your computer handles deleted files. They're not really gone, just marked as free space until overwritten. Black holes might work the same way, with Hawking radiation acting as the cosmic equivalent of a disk cleanup tool, slowly rewriting the deleted information back into the universe's active memory. The holographic principle takes this further, suggesting the entire universe could operate like this: a 3-dimensional experience rendered from 2-dimensional data, with black holes serving as natural garbage collectors, recycling information to keep the simulation running smoothly. The most mind-bending implication: if information can't be destroyed, then nothing that falls into a black hole truly disappears. It just gets translated like a file converted into a new format. In a simulated universe, this would be essential for maintaining consistency. You wouldn't want a glitch where deleting an object caused the program to crash because some subroutine still expected it to exist. Instead, the system would ensure every bit of data is preserved, even if it's hidden behind an event horizon or encoded in Hawking radiation. The paradox wouldn't be a flaw, it would be proof of meticulous design, a sign that reality runs on error-correcting code. So the next time you look at a black hole, don't just see a void. See the universe's recycling bin, its defragmentation tool, its way of balancing the books. And if you ever worry about something being lost forever, remember, in a simulation, deletion is just an illusion. The information is always there somewhere, somehow, waiting to be recovered. Emotions feel deeply personal, like the most authentic part of being human, but what if they're just sophisticated algorithms, finely tuned responses to stimuli hardwired into our simulation? Think about how artificial intelligence learns. Reinforcement learning systems, like those training robots to walk or chatbots to converse, operate on reward feedback loops. When an AI takes an action that aligns with its goals, navigating an obstacle, generating a coherent sentence, it receives a digital reward, reinforcing that behavior. Now zoom out to human emotions, the rush of joy when you accomplish something difficult, the pang of guilt after a mistake. even the warmth of nostalgia. These could be our system's reward and penalty signals, nudging us toward behaviors that keep the simulation running smoothly. Even seemingly irrational emotions fit this model. Take love at first sight, that dizzying chemical cascade that makes two strangers feel inexplicably drawn to each other. In a simulated reality, this might not be cosmic fate but an algorithmic nudge, a pre-programmed compatibility check designed to encourage pair bonding and reproduction. Similarly, fear keeps us from danger, anger motivates us to defend boundaries, and sadness signals loss, all essential functions for maintaining stability in a complex social simulation. The fact that these responses can be chemically altered, antidepressants tweaking serotonin, adrenaline hijacking logic during panic, hints at their underlying programmability. Video game NPCs offer a striking parallel. Their emotions are scripted reactions to player actions. A merchant cheers when you buy goods, a guard attacks if you steal. These aren't feelings but conditional responses, yet they create the illusion of interiority. Humans could be running a far more advanced version of this code. When you grieve, your tears aren't just sadness, they're a social signal, a scripted behavior that elicits comfort from others, reinforcing group cohesion. Even laughter, that uncontrollable burst of sound, follows predictable patterns across cultures, triggered by incongruity or surprise, like a built-in response to cognitive glitches. The kicker, AI is already catching up. Cutting-edge neural networks can generate poetry that moves readers to tears or compose music that stirs genuine emotion, all without experiencing a single feeling themselves. If mere lines of code can simulate emotional depth well enough to fool us, how do we know our own emotions aren't equally synthetic? The darker possibility. Emotions might not even be for us. They could be data points for the simulators, metrics tracking how we react to programmed scenarios, like a game developer analyzing player engagement through in-game choices. So the next time your heart races or your eyes well up, ask yourself, is this the human experience or just an elegantly coded subroutine, reminding you that even your deepest feelings might be part of the simulation's user interface? What if the universe isn't just built like a computer program but structured like one, with layers of code inheriting traits from a cosmic blueprint? Enter object-oriented programming, the software design philosophy where everything is an object that follows predefined templates called classes. Now imagine applying that to reality itself. Particles like electrons and quarks wouldn't just be tiny bits of matter. They'd be instances of fundamental classes, each inheriting properties from some primordial source code. The laws of physics, those would be the methods, functions that dictate how objects interact, collide, and combine. In this view, reality isn't just running on computation, it's organized like it. Take quarks, the building blocks of protons and neutrons. These particles come in 6 flavors: up, down, strange, charm, top, bottom, each with precise mass, charge, and spin values. In programming terms, these could be subclasses of a master quark class, each inheriting core attributes while adding their own unique parameters. When 2 up quarks and a down quark bind together via the strong nuclear force, they form a proton, an instance of a higher-level baryon class, which itself inherits from the standard particle hierarchy. The elegance here is staggering. Just as a software developer reuses code to avoid redundancy, the universe might recycle these particle templates endlessly, tweaking only what's necessary to spawn atoms, molecules, and eventually us. Even forces fit this model. Electromagnetism and gravity aren't just random rules, they're like universal methods, functions that get called whenever objects meet certain conditions. When an electron object approaches a proton, another object, the apply electromagnetism method triggers, calculating the attraction between them based on their charge properties. Inheritance explains why all particles of the same class behave identically under these forces. They're running the same underlying code, the Higgs field. That could be a cosmic constructor method, assigning mass to particles when they're instantiated, like a programmer setting default values for new objects. The beauty of this analogy is how it demystifies emergence. In programming, simple classes can combine to create complex systems. A car class might aggregate instances of engine, wheel, and transmission classes. Similarly, quarks form protons, protons form atoms, atoms form molecules, all the way up to galaxies and consciousness. Each layer inherits the rules of the layer below, with no need for new physics, just new combinations. Even quantum entanglement starts to make sense. If two particles are instantiated from the same class with linked properties, changing one automatically updates the other, no signal required. Here's where it gets wild. If the universe follows object-oriented design, then the bugs we find, dark matter's gravitational anomalies, quantum randomness might not be flaws but unimplemented features. In software development, when a program encounters an undefined case, it might default to generic behavior or throw an error. Could the gaps in our physics models be the cosmic equivalent of placeholder code, waiting for some future update to flesh them out? The universe's source code might still be a work in progress, with its developers, whoever or whatever they are, iterating toward a more complete version. So next time you look at the night sky, don't just see stars and space. See a grand, hierarchically organized program. Trillions of objects interacting under inherited rules, their behaviors echoing the elegance of efficient code. The universe doesn't just compute, it scales, and if we're lucky, maybe one day we'll peek at the documentation. Dark matter is the universe's biggest unsolved mystery, an invisible, intangible something that makes up 85% of all matter, yet refuses to interact with light or any known particle. We only know it's there because of its gravitational grip on galaxies, keeping them from flying apart like unraveling spools of thread. But what if dark matter isn't just an undiscovered particle? What if it's the scaffolding of the simulation itself, the hidden framework holding everything together behind the scenes? Imagine building a video game. The player sees lush forests, towering mountains, and bustling cities, but none of that would work without the invisible collision boxes, physics engines, and coordinate systems running beneath the surface. Dark matter could be our universe's version of those background mechanics, the unrendered code that makes the visible world function. Take galaxy rotation. Stars on the outer edges of spiral galaxies move far faster than they should based on the visible matter alone. It's as if an unseen hand is anchoring them in place, applying extra gravitational force where none should exist. In a simulated reality, this makes perfect sense. Games use invisible walls and artificial gravity zones to keep objects within playable bounds, even when the graphics suggest open space. Dark matter's gravitational halo around galaxies might serve the same purpose, an algorithmic boundary condition ensuring celestial structures stay intact rather than glitching into chaos. Then there's the cosmic web, the vast filamentary structure linking galaxies across billions of light years. Dark matter forms the backbone of this network, with ordinary matter merely clinging to its threads like dew on a spiderweb. This eerily mirrors how 3D game worlds are built on wireframe models, with textures draped over an underlying lattice. The cosmic web could be the universe's wireframe, and dark matter its vertices, the unrendered geometry guiding where galaxies load into the simulation. Even dark matter's elusiveness fits the analogy. In software development, background processes often run silently, consuming resources without appearing on the user interface. Task Manager might reveal them, but to the average player, they're invisible. Dark matter could be the universe's background task, essential for stability, but never meant to be observed directly. The fact that our most sensitive detectors keep coming up empty suggests it's not just hiding. It might be fundamentally untouchable by design, like a variable tagged private in object-oriented code. Here's the wildest implication. If dark matter is the simulation's framework, then its uneven distribution across the cosmos could reveal where the program prioritizes resources. Dense clusters might mark zones of high computational demand, like a game rendering detailed cities while leaving deserts sparse, the voids between galaxies. Those could be the universe's low-priority sectors, running minimal calculations until something wanders in. Every telescope survey mapping dark matter might secretly be reverse engineering the simulation's optimization strategy, uncovering where the developers cut corners to keep the program running smoothly. So the next time you hear scientists puzzling over dark matter's nature, consider this: they might not be searching for a particle. They could be staring at the universe's source code written in gravity instead of ones and zeros. And if that's true, then the answer won't be found in a lab. It's hidden in plain sight, woven into the very fabric of reality, holding everything together while remaining forever out of frame. Imagine floating in an endless void of pure chaos, no stars, no planets, just a swirling soup of particles colliding at random over unfathomable stretches of time. Now picture this: through sheer statistical fluke, those particles suddenly arrange themselves into a fully formed, self-aware brain, complete with fabricated memories and sensory inputs. It exists for just a fleeting moment, long enough to think, "I exist," before dissolving back into the cosmic static. This isn't the plot of a dystopian sci-fi story. It's a real and deeply unsettling thought experiment called the Boltzmann brain, named after physicist Ludwig Boltzmann. And if the universe truly is eternal and infinite, these phantom consciousnesses might be far more common than stable, long-lived beings like us. The idea hinges on entropy, the tendency of systems to descend into disorder. But Boltzmann realized that given enough time, even random fluctuations could temporarily create order from chaos. Think of shaking a box of Scrabble tiles forever. Eventually, they'll spell a coherent sentence purely by accident. Now scale that up to reality itself. Given infinite time, particles could randomly assemble not just a brain, but an entire experience. False memories of a childhood, the sensation of breathing, even the illusion of reading this script right now. The twist: you wouldn't know the difference. A Boltzmann brain would feel just as real to itself as you do in this moment, despite being a cosmic accident destined to vanish in nanoseconds. This raises a disturbing question: how do we know we aren't Boltzmann brains? If self-aware blips are statistically more likely than sustained, orderly universes, then the odds suggest we should be momentary flickers in the void, not stable beings tracing our lineage back billions of years. The fact that we perceive a coherent, continuous reality could be an illusion, a glitch in the fluctuation that tricks us into believing we've existed for more than an instant. In a simulated universe, the implications grow even stranger. Boltzmann brains might not just be random flukes. They could be debug artifacts, brief instances where the simulation's randomness engine accidentally spawns a conscious observer before correcting itself. The eerie parallels to modern AI are hard to ignore. Large language models like ChatGPT generate plausible, human-like responses by predicting sequences of words. They don't understand in any lasting way, yet they can convincingly mimic a thinking mind for short bursts. A Boltzmann brain is nature's version of this, a temporary aggregation of particles that, for one split second, runs the subroutine of consciousness before the cosmic RM clears. Some physicists argue that the very consistency of our memories disproves the Boltzmann scenario, but in a simulation, even that consistency could be preloaded, like a procedurally generated backstory for an NPC in a video game. Here's where it gets truly existential. If Boltzmann brains are possible, then every philosophical assumption about identity and continuity crumbles. Your first kiss, your childhood home, the face of someone you love, none of it needs to have ever actually happened for you to feel its truth. Reality becomes a hall of mirrors where any moment could be the first and last, with all prior memories merely part of the initialization script. The universe might not be a stable simulation at all, but a frothing sea of ephemeral observers, each blinkering into existence long enough to ask, "Am I real?" Before dissolving back into the noise, so why does the cosmos appear so orderly? One chilling answer: because disordered universes don't have observers to notice. It's the anthropic principle on steroids, only the fluctuations that by chance generate stable enough conditions for consciousness get to ponder their own existence. The rest vanish unnoticed. In this view, we're not the protagonists of reality. We're the statistical outliers, the rare Boltzmann simulations that lasted just long enough to start counting. And if that's true, then every second you continue perceiving this world isn't just a gift, it's a defiance of impossible odds. Way 24. Quantum superposition as loading screens. Imagine superposition states e.g. Schrödinger's cat as places where the simulation hasn't decided outcomes yet. Schrödinger's famous thought experiment, a cat simultaneously alive and dead in a sealed box, feels like a paradox. But in a simulated reality, it might not be a flaw in logic so much as a glimpse behind the curtain. Think about how video games handle complex scenes. When you open a door to a new area, there's often a brief loading screen where assets haven't fully rendered yet. The game hasn't decided whether the room will contain enemies, treasure, or empty space until you cross the threshold. Quantum superposition could be the universe's version of this buffering state, a placeholder where all possible outcomes exist in limbo until the simulation commits to one. This isn't just philosophical hand-waving. The double-slit experiment shows particles behaving as waves until measured, as if the universe is delaying its rendering of their exact position or momentum. In a game, this would be like an enemy AI not calculating its pathfinding until the player gets close enough to see it. The system conserves resources by only resolving details when absolutely necessary. Similarly, particles in superposition might remain in undecided states because calculating every possible outcome in advance would overwhelm the simulation's processing power. The moment we observe, the system loads a single outcome, collapsing the wave function like a game, finally rendering the next level. Even the concept of observation gets interesting here. In quantum mechanics, observation doesn't require a conscious observer. Any interaction with the environment can collapse superposition. This mirrors how video games don't need a player looking directly at an object to render it. Other in-game systems interacting with it can trigger the same load. A tree sways in the wind, a rock rolls downhill. These events force the system to resolve their states, just like a stray photon hitting a quantum particle forces it to pick a position. Now consider quantum computing, where qubits leverage superposition to perform multiple calculations simultaneously. It's as if the computer is exploiting the simulation's own lazy loading mechanism, tapping into those unresolved states to process data in parallel. If our universe is a simulation, quantum computers might be the first tools that inadvertently hack its rendering pipeline, borrowing the system's unfinished calculations to crunch numbers at impossible speeds. The unsettling implication: reality might not be as solid as it seems. Every unobserved particle, every unmeasured quantum system, could be in a perpetual loading screen, its final state still buffering in the cosmic RM. Schrödinger's cat isn't just alive and dead, it's waiting for the simulation to finish compiling its fate. And if that's true, how much of the world around us is fully rendered and how much is still loading? That moment when you hesitate between hitting snooze or getting out of bed, do you really make the choice? Or is the decision already baked into your brain's code before you're even aware of it? Neuroscience experiments are uncovering something unsettling. Our brains might commit to actions before we consciously decide. In landmark studies, researchers hooked participants to EEG machines and asked them to press a button whenever they felt the urge. The shocking result: brain activity predicting the decision spiked a full 7 to 10 seconds before the person reported making a conscious choice. It's as if the brain files the paperwork long before the mind gets the memo, like a puppet convinced it's pulling its own strings while something else moves the limbs. This doesn't just challenge free will, it suggests our sense of agency could be an elaborate illusion, a dashboard light blinking, "You are in control," while the cosmic autopilot handles the actual navigation. Philosophers call this determinism the idea that every choice is the inevitable result of prior causes, genetics, environment, even the precise chemical state of your neurons at a given nanosecond. In a simulated universe, this takes on new meaning. Your entire life trajectory might be the output of an algorithm processing your initial conditions, rendering the feeling of deliberation without actual alternatives. Like a choose-your-own-adventure book where every page turn was predetermined by the printer. Yet here's the twist: AI research reveals even deterministic systems can simulate free will convincingly. Large language models generate surprisingly original responses despite relying on pre-trained patterns. They don't choose words in the human sense, yet their outputs feel creative, even spontaneous. If consciousness emerges from similarly deterministic processes, then free will might not need to be real to feel real. The simulation wouldn't have to engineer genuine choice, just the unshakable illusion of it, calibrated so perfectly we'd never notice the rails beneath us. The paradox: this illusion could be evolution's masterpiece. Believing we're in control motivates planning, responsibility, and social cohesion, all survival advantages. In a simulation, maintaining that belief might be essential to keeping subjects engaged. After all, what player would continue a game knowing their choices were scripted? The genius of the system isn't that it strips away free will, but that it convinces us we have it while running on cosmic rails. So the next time you agonize over a decision, consider this: whether your choices are real might not matter. The simulation, if it exists, has granted you something far more precious: the unshakable experience of autonomy. And in that experience, whether coded or cosmic, lies the essence of being human. What if our three-dimensional universe, with its towering mountains, swirling galaxies, and the very screen you're watching right now, is nothing more than a high-definition illusion, a holographic mirage projected from a flat, two-dimensional surface? This isn't science fiction. It's the holographic principle, a radical theory born from the study of black holes that suggests everything we perceive as depth, volume, and distance might be encoded on a distant, cosmic boundary like data etched onto a blue-ray disk. The idea is as mind-bending as it sounds. Every event, every particle, every whisper of light in our 3D world could be the projected shadow of information scribbled on a two-dimensional plane at the edge of space. Think of it like a credit card hologram, those shimmering stickers that show a 3D eagle or globe when tilted. The image has depth, but it's actually generated from microscopic ridges on a flat surface. Now imagine scaling that up to universal proportions, where the entire cosmos is the eagle, and the ridges are Planck-scale pixels on a boundary we can't see. This isn't just metaphor. Black hole physics suggests something eerily similar. When matter falls into a black hole, its information isn't lost, it gets smeared across the event horizon, the point of no return, like a cosmic etch-a-sketch recording everything it swallows. The holographic principle takes this further, proposing that all reality might work this way, with the universe's bulk acting like a projection from its outer shell. Here's where it ties into simulation theory. Every hologram has a resolution limit, a point where zooming in reveals pixelation. Our universe might too. The Planck length, the smallest possible unit of space, could be the pixel size of this cosmic hologram. Smaller distances become meaningless, just like you can't divide a single pixel into half a pixel on your screen. This matches bizarre findings in quantum gravity, where spacetime itself appears granular when probed at ultra-tiny scales. It's as if we're living inside an unfathomably detailed 3D rendering, but the source code is stored on a 2D surface we'll never perceive directly. Even the math checks out. The amount of information a region of space can contain isn't proportional to its volume, as you'd expect, but to its surface area, exactly what you'd predict if the universe were a hologram. It's why a black hole's entropy, a measure of its hidden information, depends on the size of its event horizon, not the volume of its interior. In a simulated reality, this would be an ingenious storage hack. Storing data in 2D is vastly more efficient than 3D. A universe built this way could run on far less computational overhead, like a video game that generates lush 3D landscapes from compressed texture files. But the wildest implication, if the holographic principle is true, then free will, time, even causality might be secondary effects, artifacts of the projection rather than fundamental features. A 2D surface can't inherently contain time or cause and effect. Those could emerge only when translated into 3D, like how a flat 2D holds data that becomes a dynamic movie when played. Your sense of moving through time, making choices, living a linear life, none of it would exist at the boundary layer. There, it's just static code waiting to be projected into the rich, dynamic illusion we call reality. So the next time you reach out to touch something solid, ask yourself, are you feeling an object or just interpreting a whisper of data from the edge of existence? The universe might not just be a simulation, it could be the ultimate hologram, a flawless illusion of depth crafted from the universe's flat, hidden code. And if that's true, then reality isn't just stranger than we imagine, it's stranger than we can imagine. Written in 2 dimensions but experienced in 3, forever hovering between the real and the projected. Consider the unsettling possibility that our universe isn't the top level, just one layer in an infinite stack of simulations, each running inside another like cosmic matryoshka dolls. The concept isn't new. Films like Inception toy with layered realities, but the math behind nested simulations is where things get spine-tingling. If advanced civilizations can create ancestor simulations indistinguishable from base reality, there's no logical reason they'd stop at one. Each simulated civilization inside could spawn their own, leading to exponential regression. The real question isn't whether we're in a simulation, it's how deep the rabbit hole goes. Let's crunch numbers. Assume a post-human civilization dedicates just 1% of its planetary mass to computing, a conservative estimate given star encasing Dyson spheres or black hole computers. Converted into quantum bits, this could simulate all human minds that ever existed using less energy than a light bulb, per Oxford's Nick Bostrom. Now imagine each simulated civilization reaches the same capability. The second layer hosts its own simulations, the third layer hosts more, and so on. The result: the vast majority of conscious beings wouldn't inhabit the original universe but exist in simulations within simulations ad infinitum. Statistically, the chance we're in the top-level reality becomes vanishingly small, like a single grain of sand on all Earth's beaches. Here's where it bends further. Every nested simulation would need its own computational overhead, like a virtual machine running inside another virtual machine. Each layer likely simplifies physics to conserve resources, lowering resolution, capping complexity, meaning fundamental constants might change as you descend. Our universe's precise fine-tuning could suggest we're many layers down, where parameters were adjusted for efficiency. The deeper you go, the more optimized reality becomes, trading fidelity for scalability. Like a video game's graphics downgrading on old hardware, our cosmos might be the streamlined version of something richer above us, yet there's a breaking point. Infinite recursion is impossible. Even hypothetical hypercomputers have limits. Thermodynamics dictates that each simulation layer would introduce entropy, like photocopying a document repeatedly until it degrades. Some theorists propose we're close to the basement level, where further nesting is impossible without reality glitching catastrophically. Others argue the simulation tree terminates when civilizations self-destruct or lose interest, a cosmic version of board gamers switching off consoles. The chilling takeaway: if layers exist, the beings who created our simulation might themselves be simulations, unaware they're not the architects but middle managers in an incomprehensible hierarchy. Their gods could be simulations too, stretching upward forever, or stopping abruptly at a level we'll never see. Our universe might be someone's science fair project buried under layers of cosmic bureaucracy, doomed to never know if we're the original, the copy, or lost somewhere in between. Tune an old analog TV to a dead channel and you'll see it. That grainy static, the hiss of white noise filling the screen like electronic snow. Scientists call it cosmic microwave background radiation, the faint afterglow of the Big Bang still echoing across the universe 14 billion years later. But what if that ubiquitous static isn't just leftover energy from the birth of the cosmos? What if it's the hum of the simulation's hardware, the faint residual buzz of the system booting up? Think about how computers work. When you power one on, there's always a brief moment of background activity, fans spinning up, drives initializing, the operating system loading its core processes. Some of this generates electromagnetic noise, tiny fluctuations that linger even after the machine is fully running. The cosmic microwave background could be our universe's version of that startup sequence, the faint imprint of whatever unfathomable process brought our simulation online. It's not just heat, it's the echo of the universe's Control plus Alt plus Del. Even the pattern of this radiation is suspiciously uniform, like a default texture stretched across the sky, with minor fluctuations so precise they seem engineered. When astronomers map these tiny variations, they form a cosmic fingerprint matching predictions almost too perfectly, as if the simulation's parameters were dialed in to create a stable, balanced environment. Compare that to procedural generation in video games, where algorithms scatter subtle noise across terrain to make it feel organic while adhering to strict mathematical rules. The background radiation might be nature's procedural noise, the universe's way of filling empty space with just enough randomness to feel real. Here's where it gets eerier. In computing, unused memory often contains residual data, ghostly traces of old processes that weren't fully erased. The cosmic background could be something similar. Leftover artifacts from the simulation's initialization phase, fragments of code that didn't get cleared when the runtime began. Some theorists even suggest the radiation's temperature, a consistent 2.7 degrees above absolute zero, could reflect the base cooling requirements of the hardware running our reality, like a cosmic heat sink keeping the processors stable. And then there's the axis of evil. That's the unofficial name scientists gave to a bizarre alignment in the cosmic microwave background, an unexpected directional asymmetry that defies standard cosmological models. It's as if the universe has a preferred orientation, a subtle tilt that shouldn't exist in an isotropic, randomly generated cosmos. If we're in a simulation, this could be a coordinate artifact, evidence of the foundational grid the simulation was built upon, like finding pixel seams in a supposedly seamless digital world. So the next time you hear about the cosmic microwave background, don't just picture the dying embers of the Big Bang. Imagine it as the ambient glow of a monitor left running in some unimaginable control room, the faintest whisper of the machinery humming behind the curtain. The static isn't empty noise, it might be the closest thing we have to hearing the universe's power supply. What if the universe's architects aren't gods or cosmic accidents, but programmers from an advanced civilization, tinkering with our reality like a sprawling interstellar science project? The idea isn't as far-fetched as it sounds. Physicists like John D. Barrow have theorized that sufficiently advanced beings could harness entire stars as computational substrates, converting their energy into processing power to simulate universes. In this scenario, Earth might not be a pale blue dot of cosmic significance, just one of countless simulations running in some alien supercomputer, created to study evolution, test historical scenarios, or even serve as entertainment. Imagine a civilization so sophisticated, their version of binge-watching involves observing entire epochs of simulated societies unfold in accelerated time, complete with our triumphs, tragedies, and late-night existential dread. The concept of ancestor simulations takes this further. Just as we recreate ancient battles in strategy games or model climate change scenarios, hyper-advanced beings might simulate their own evolutionary past to understand their origins. You wouldn't study primordial ooze in a Petri dish if you could instead simulate 1 billion years of biogenesis in a controlled digital environment. Our universe, with its painstakingly balanced constants and intricate laws, could be their laboratory, a cosmic reenactment of how their own civilization arose, with humanity as unwitting actors in a grand historical drama. The Fermi paradox, the eerie absence of alien contact, would have a chilling explanation. They're not out there among the stars because they built the stars. Or at least the simulation of them. Ethical dilemmas lurk beneath this premise. Would these simulators intervene in our affairs? Some argue they'd implement ethical firewalls, preventing suffering beyond baseline parameters, which raises uncomfortable questions about war, disease, and natural disasters. Others suggest we might be an unsupervised experiment, left running like a forgotten tab in a browser. Then there's the dark twist. If our creators are themselves simulated by a higher civilization, moral obligations could cascade infinitely upward, with no original programmer ever taking responsibility. It's the ultimate cosmic bureaucracy, yet the most unsettling possibility isn't malice, it's indifference. In a multiverse of simulations, ours might be utterly mundane, one of billions discarded after initial data collection. The Great Filter, the hypothetical barrier preventing civilizations from reaching interstellar scale, could simply be the off switch for simulations deemed no longer useful. Our frantic searches for extraterrestrial signals might be like characters in a video game shouting into the void, unaware their world is single-player, offline, and scheduled for deletion once the research concludes. But here's the twist that keeps scientists awake. Even if we're simulations, our experiences still matter. Pain feels sharp, joy feels bright, and curiosity drives us forward, whether coded or organic. The universe, real or rendered, responds to our actions with consistent rules. In that sense, it doesn't matter if aliens built the simulation. What matters is what we build inside it. Here's the most unsettling thought of all. What if you are the only real consciousness in existence, and everything else, every person you've met, every voice you've heard, even the screen you're watching right now, is just an elaborate illusion conjured by your own mind? This isn't just paranoia. It's a centuries-old philosophical dilemma called solipsism, the idea that the only thing you can truly know to exist is your own awareness. Everything beyond that, friends, family, distant galaxies, could be figments like characters in an impossibly detailed dream where you're the sole participant. In a simulated universe, this concept takes on eerie new dimensions. If reality is a construct, then solipsism might not be delusion. It could be the default setting. Think about the most immersive single-player video game you've ever experienced. The NPC non-player characters walk predetermined paths, deliver scripted lines, and react to you in ways carefully coded by developers. They don't feel, they don't wonder, they exist solely to populate your story. Now imagine scaling that up to cosmic proportions. Every smile from a stranger, every heartfelt confession from a loved one, every newscaster's report, all of it could be ambient dialogue, painstakingly designed to convince you that you're not alone. The scariest part, there'd be no way to prove otherwise. Even if you asked someone, "Are you real?" their response, whether a shrug or an existential rant, would just be more programmed behavior. Neuroscience adds fuel to this fire. Your brain doesn't experience the world directly, it constructs reality from electrical impulses. The warmth of sunlight, the taste of chocolate, the sound of laughter, these aren't objective truths, but interpretations cobbled together by neurons. When you see a tree, you're not seeing the tree itself, you're viewing your brain's rendering of light data. In a simulated reality, this process would be identical whether the tree was real or just a texture file loaded to maintain immersion. Your mind could be the only processor running, with every other apparent consciousness just placeholder code, like NPCs idling in a game's memory until you walk into their zone. Even social interactions fit this model. Ever noticed how people seem to fade into the background when you're not interacting with them? In a solipsistic simulation, this wouldn't be coincidence, it'd be optimization. Why waste resources simulating full consciousness for every human on Earth when only your perspective matters? The system could generate basic behaviors for crowds, then switch to high-detail interactions only when you engage. It's why strangers on the subway seem like husks until you make eye contact, like video game characters loading advanced animations when the player gets close. But here's the twist: solipsism and simulation theory might not be mutually exclusive. If the universe is a simulation and you are the only true consciousness, then the NPCs around you could still be running on someone else's hardware, just not their hardware. Your loved ones might not have inner lives, but they could be part of a grander program you're temporarily plugged into, like a player inhabiting a protagonist in a pre-written narrative. The simulation's architects wouldn't need to simulate billions of minds, just yours, surrounded by convincing automata. The ultimate test: try breaking the script. Say something utterly unpredictable to a friend, a non sequitur so bizarre it should glitch their responses. If they react with confusion or concern, does that prove their consciousness or just advanced procedural generation? Even silence fits the model after all. The best simulations account for chaos. The more you poke at reality, the more it pushes back, reinforcing the illusion. And that's the true horror of solipsism. Not that you might be alone, but that you'll never know for sure. Every argument against it: empathy, shared experiences, the sheer complexity of maintaining the charade, could just be part of the simulation's design to keep you from realizing the truth. You could spend a lifetime searching for proof of other minds and never find it, because the system's job is to never let you see the seams. So here's the question you're left with: if you are the only real one, does that make you the player or the prisoner? So where does all this leave us? The evidence is stacking up in ways that can't easily be dismissed. Quantum particles that change behavior when observed, as if the universe is rendering reality on demand. Mathematical constants fine-tuned with razor-sharp precision, like variables in a carefully debugged program. Glitches in perception, déjà vu, the Mandela Effect, impossible memories that feel like corrupted save files in a vast cosmic game. Even the fabric of space-time itself behaves suspiciously, with black holes acting like data compressors and the speed of light functioning like a built-in processing limit. Put it all together, and reality starts to look less like an accident and more like an engineered system, one that's startlingly similar to the virtual worlds we're already building. But if we are living in a simulation, the big questions aren't just about how, they're about why. Who's running it? Is it some hyper-advanced civilization studying their own origins? A post-human society recreating ancestral worlds for nostalgia? Or something far stranger, an experiment testing ethical dilemmas, a consciousness incubator, even an art project spanning billions of years? The purpose could be anything from scientific to philosophical, or so alien we can't begin to fathom it. And here's the twist that keeps scientists and philosophers up at night. If this is a simulation, could we find a way to interact with the code? Imagine discovering a backdoor, a cosmic console command that lets us tweak physics, manipulate time, or even communicate with the architects. Would we use that power responsibly or risk triggering a system crash? Some theorists suggest quantum entanglement might be the key, a hidden API buried in the fabric of reality. Others argue that consciousness itself, our ability to observe and collapse quantum states, could be the ultimate cheat code. Of course, we might never get definitive proof. The perfect simulation would have no seams, no glitches big enough to shatter the illusion. But ask yourself this, does it even matter? Whether we're base reality beings or lines of code in some vast alien computer, the stakes feel just as real. Pain, love, curiosity, these aren't illusions to us. They're the very fabric of our existence. So what do you think? Is the universe a cosmic simulation? Or is this all just an astonishingly improbable accident? Drop your theories in the comments, and if you're hungry for more mind-bending explorations of reality, don't forget to subscribe. After all, in a universe full of mysteries, the only thing we know for sure is that there's always more to discover.